this is the control room, and that's the equipment room. And so if you were going in either room, this stop sign makes you stop and think about what's allowed, because it's not really allowed for engineers to start tinkering around with their systems in the workroom back here when the GBT is operational, because they might inadvertently tinker in the wrong, they might disconnect a cable or in some way mess things up for the astronomer that's actually using the telescope.
That would be bad and bad. So,
the control room and this workroom here were finished well before the telescope was. So engineers had a different habit. They were testing and prototyping, and we were simulating and so forth. And so they were just used to being in there working whenever they felt like it. So we had to change the rules, and this helps. Just this little sign there helps people remind themselves, oh, I better not do that right now. So we're going to go in, and I would like to have you step over the bottom of the door. So there's a brass strip on the bottom, and just step over it as you come in rather than stepping on it. Okay?
Why can't we step on it?
Because I said don't.
Good job. I've been in here before.
No way. Were you here last year?
Yes.
Okay.
I've been in here.
You remember it?
Yeah, to see if there was any effects to it.
Yeah, come on in, look around, walk around a little bit, spread out a little bit. You can do this. You can come through.
Oh, I can come over there?
Yeah, come on over.
Okay. Well.
Okay. Maybe she gets everybody in. Yeah, you didn't miss the
You wanna shut the door?
thing, right? Chair over this way, George.
All the way down. So see, when this door is like that, it's like it doesn't exist. It's such a tight seal, it's part of the wall. And so that we don't want to wear out the bottom of it, or else it won't have a nice tight seal. So that's why.
If he starts giving you too much trouble, just let me know.
It's fine.
I think he asked you a million questions the last time we came.
Cameras are okay, right?
Cameras are okay. Yeah. Look at all those seats over there. It's like a party was going on over there. Hi, Kevin.
Don't say anything.
How are you? All right, here you are, GBT Control Room. This is Kevin, the grumpy telescope operator I was telling you about. And he's here until 7.
7 o'clock.
Yeah, and then he gets to go home, and somebody else comes on.
And then I come back and do it again.
You do. But who starts at 7 p.m.? Okay. Crows. Oh, okay. Okay.
How long is the shift? Kevin, how long is your shift? 12 hours?
Long time being.
Yes, it is.
What are you looking at today?
What are we looking at today?
It's Stark. He's running his elevated. He's right here.
Okay.
276.
All right.
Common structure and all that.
Oh, cosmic. No, cosmic.
Cosmic.
Can I click on it or not?
Go ahead. Give you a list. This is the same one that's available. Subscribe to this by a Twitter account.
Shoot.
And,
I messed
get
it up,
your
Ken.
schedule. That's really nice.
Yeah.
Each one of the things, the new things that are added, I can get to.
Oh, there it is. All right, so it says blah blah. That's okay. So this is so let's go back to that title again. What's the title? It's a project that does it's for star formation. Got a ton of people on it, all over. It's called Tracking Star Formation Efficiency as a Function of Cosmic Structure. So let's see if they talk about the cosmic web. Blah blah. Limits, most galaxies. So they're looking at galaxies actually to try to measure star formation rate in them. And they're trying to figure out how fast gas falls on these galaxies. Galaxies accrete gas onto them, and that spurs star formation. And so I think because they're talking about cosmic scales, they are actually looking back pretty far. They're doing 132 galaxies, 127 galaxies, and they've requested 191 hours of telescope time. So, it's a big, big collaboration of people. There's probably 10 people on this list. And I don't know who's anybody logged in with you, or you just... Oh, Starkey. Okay. And this is the pass band of the receiver. And you can see a little spike in there. That's probably H1 right there. So that's not what they look at exactly. They kind of zoom in on that, but that's a diagnostic tool for Kevin to make sure things look right.
Do the galaxies ever show up on the pictures, ever show up on the screen or any of the galaxies?
So they're measuring the hydrogen content in these galaxies, and what they get are graphs that you can measure the area under the curve and find out how much. You can compare what you're seeing perhaps along the axis of some of the galaxies, but they're not getting a pretty picture.
It's almost like an Excel sheet in the down that they can see.
Yeah, it's a bunch of numbers, but yeah, it's a bunch of numbers. It's called a FITS file, even though it's a graph. Even though that's an image transport system, it's like a data cube with velocity versus amplitude versus something in a third dimension there. Yeah, I don't know much about it. And here we have, what do we have up here?
That's all recording stuff.
Cool. So what happens nowadays that's different from the old days is that block diagrams like that are actually interactive. So you can pull up a block diagram for a receiver and you can click on it and find out what the levels are without taking your voltmeter back and hooking it into all these external ports. So that used to be the way we did things. In terms of the display screens you see here, the 20-meter screens are displayed over on the far right in the back. And those are what the operator sees, which are similar to what y'all saw if you were in the 20-meter imaging session yesterday afternoon. So those of you that were in that know that you could select an object from the sky map, then you would select the kind of observing you wanted to do, and so forth and so on, and then the telescope would move there and do it. And so that's kind of what you're seeing here. You're seeing where the telescope is that red bullseye in the sky, and it's just sampling the noise that's coming into the telescope. So nobody's using it right now. It's not pointing anywhere. It's not collecting any data at the moment. But the rest of it is for Kevin to use, because if it hangs up, then he notices, you'll see some error things pop up, and he can get us back up and running again. The middle screen here is for the 140-foot, is it? Both of these now?
Both of them.
Okay. So both of these screens are for the 140-foot telescope, sometimes called the 43-meter by European people. And this telescope is being readied. It's being commissioned to become a tracking station for Radio Astron, which is a Russian radio telescope in orbit about the Earth that will be used and is used in conjunction with telescopes on the ground, including the GBT. So this is a very, 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 very long baseline interferometer. And, so you see there the position of the telescope. I don't know, Kevin, tell me what's going on here.
0 and 38, so your polar axis.
Okay, so you're pointing
Your
straight up.
azimuth, right, and your declination,
Yeah.
and your elevation.
And then these are actually things that you can click and command on the telescope on this
Maintenance, you can control
this
everything.
VNC.
Yep. You still have to have that up to control the 140 foot, but you
Okay.
need this up to watch it.
Yeah.
When
So this is
you
your
can still
watching
use that.
screen. That's your controlling screen.
Yeah.
Got it.
And you can still watch it from here, but they decided to do something similar to this.
Okay. And then up here is the control for the 45-foot telescope that hasn't been doing much of anything lately. It's supposed to be looking at the sun, but that hasn't been happening for quite a while. Now these bars that you see going up and down are indicating that the telescope is moving. So that's the GBT. This is all GBT right here, all these 4 screens. And the bars on this little window right there are showing the forces on the motors, the torques on the motors as the telescope moves around. So that's a very cool little graphic to watch. This is a picture of the dish, and all the red on there is just showing you that the active surface is not on. It's turned off. It's not needed for this experiment. If it were turned on, it would be green, except for places where there were broken actuators.
How do you move it? How do you move the dish with that keyboard? Or?
It's actually done through scripts that are written ahead of
Oh, I
time,
see.
usually. Kevin can move it via this or
I thought you had the big
that. Joystick.
big joystick, or not joystick.
But yeah, it's an observer. This group of people that is doing this galaxy survey has written instructions in the proper language, a script we call it, and then that script has been validated, and then that script has been uploaded and has been activated to tell the telescope what to do.
It's not a Unix-based system.
Yeah, it's Linux.
So it is Linux.
And this was all written using a programming language called TCLTK, which we now use a lot of Python now, but we were using TCLTK. Yeah.
How do they determine these of the arm on a telescope versus the traditional? I mean, is there a reason why it's pointed that way instead of the opposite way?
You see this picture of the dish here? Let's big it up again.
There, how's that?
That's just great.
Looks like a glove, don't it?
Okay. Do you see how these little arcs get smaller and smaller? That is the center of a much larger dish than we built. So if we built the much larger dish that had that as its center, then you would support the receivers with legs that rise up over the center. But that arm supports receivers above that spot. So it's like half a parabola, you know, where the radio waves are bouncing up to that spot because we didn't build the whole dish. And we did that on purpose. We didn't want these legs in the dish that form diffraction patterns and things like that. You know, anytime you put something in front of your mirror, you're going to mess things up a little bit. And so these legs in our normal, traditional radio telescopes are a problem. They create interference, they create unwanted signals and things like that.
So the angle that way would be even.
So the telescope is pointing, if you look at the top of the arm, that's where the telescope is pointing, not where the dish looks like it's
Right.
pointing, but where the arm is pointing. Yeah, good. Yes.
How many galaxies does the GBT go to?
Well, for this project, I don't know how long it lasts, but they said there were 127, but I bet they're not going to do them all. Because in order to collect enough signal from these galaxies, we have to follow them. And follow them for maybe 10 minutes or a half an hour or something, collect on that one galaxy for a while. Yeah.
How fast does the GBT move?
Okay? You can do a complete turnaround in 9 minutes. 360 degrees in 9 minutes. And it takes 8 minutes to tip all the way down. But you can do them simultaneously. It actually moves really fast. I know that doesn't sound fast, but if you were down there watching it, it looks really fast.
It looks so slow.
I know.
It's slow.
Well, wait till you see it moving that fast. You would think it was fast. You have to go down there.
When you say validate the script, they write the script and then you look at the script and say, you know, line 14, you know, we're having a problem with that. That type of validation.
It is, but it's done via the, it's done by a program.
Isn't it?
How many radio waves does the GBT go?
Let's see. Right now, the GBT is picking up 1,420,000,000 2 billion waves every second.
That's a lot.
Yes, it is.
Handful.
I'm going to let you listen to what it sounds like to listen to a cold receiver. We have a listening post here where we have microphones on the GBT in various places, and we can listen to various places on the telescope down there. So right now, Kevin has the microphones on the motors that drive the telescope around. It's a good thing to listen to. You don't want to hear them straining or something, but I'm going to turn them off right now. And instead, I'm going to play for you the sound up in the room. I showed you a picture of the room where all the receivers were. So we're going up there now by sound, and we have microphones attached to all of the different receivers. So first I'll play you the whole room
Hello?
in a minute.
Go ahead, turn it up.
Okay, turn it up?
Yep, go ahead.
Okay, here we go.
Hey.
So that's what it sounds like if you're working in there. If you have to go up and work on a receiver, that's what's going on in there. Now this is
Okay.
what the individual receivers sound like.
Oh, yeah, call me back later if you want. I'll take a look at it. Where's it at?
So that's the big L-band horn. Remember the one I could live in if I were homeless? Okay. This is X-band. It works from 10 to 12 gigahertz. It's got a smaller refrigerator. It's a smaller box. I don't think there's anything in this one. Oh, yes, there is. No, that's the same one, I think. No, it's not. It's a different one. Nothing in this one, maybe. Okay, here we go. That's pretty good. Did you do something with that with your theremin?
Yes, I used to do music like that. Can you get samples of these online?
No, but you've got it on your...
Okay.
So back behind you are all those are called back ends. This is where the data ends up. So we carry the data on fiber optic cable. Back here to the control room, and there are several rows of equipment. Some of them are spectrometers. Some are really fast samplers. So that's the sort of the back end part of the receiver system. Does anybody have questions about this room? Anything you're looking at in here or anything at all? Now's your chance.
The obvious question, what's the big red button again?
Oh, yeah, the big red button. So that's the button that you just do not ever want to have to push. That is the hard stop button for the telescope, for the motion.
What's the yellow button?
Right there. The yellow button is the easy button. So it's the button that, you know, slows things down before it stops. So that's the panic button if you ever had to stop the telescope. And they have them all over the telescope too, and they will push them in the stop position if they're going to be climbing on the telescope or something and they don't want it to move. But
And make people fall.
yeah, exactly.
Yep. Would be hard.
Exactly.
It's strong enough to walk
How
on,
often do you
isn't
ever
it?
have to use the binoculars that are out there?
Those binoculars, you know, when we built the... So that's the other thing. This is a shielded room. You're inside of a shielded room. And here's the reason why. This is an experiment you can do at home if you've got an AM radio. So I have the radio turned on. You can hear a little static, right? So take this over there to that this display and hold it up higher. Yeah, hold it up to that thing. There you go. So you can hear more sound coming into your radio. That tells you something. It tells you that this device is giving off radio waves. So we can try it on, let's see. Yeah, okay, there. Come over here and try it on this.
Can you try it on my camera?
Sure.
Oh,
Yep.
okay, I guess
I'm
now I
about to
know
place my leg.
not to ask to take it over there.
So there are lots of things in this room that give off radio waves. I mean, everything from this fluorescent light to this telephone, these computer screens.
It sounds like metal racing each other.
Yeah. That's not so bad, that's the old CRT. But if we opened up that door to let you look through the binoculars, we'd be letting all that out. If we did that, the astronomers would see that in their data, and they would have bad data for a few seconds, so we wouldn't want to do that to them. So there you have it. We do have a microwave oven in here, though that's kind of cool, because we don't get to have those around much. It's over there in the corner, and it's inside its own box. It's inside an extra box.
Oh, I see it now.
See it now?
Right here.
Yeah. So not only,
Why do you have to lock
So
the
when
microwave?
it's not locked up, and we really have to shield it. It puts out microwaves, and those microwaves are waves that we study too. So we have to keep all those microwaves in there. It's still not good enough. For a microwave oven, puts out a lot of microwaves.
See so much.
How much does it cost?
Not much. $15 or $10 or something. It's a radio.
Where
You could listen to the radio with it if you lived in a place other than here. I got this one at Walmart, but you can get them at Radio Shack. It's a radio. You can listen to it. When you're not doing this experiment, you can actually listen to the radio.
It's old technology.
It is.
From
It's
the
so
last
cute. It's
century.
so cute. Like, that's cool. What's that? Is that a walkie-talkie? Are you on the treadmill? Do you think it gives off radio waves? You want to try it? Come on and try it. Come on and try it. You asked the question. You should try it.
Test it. It's
It's an experiment.
It's true. If you ask a question,
You have to try it.
you have to try it.
Come on, let's try it. We're not going to get on it and walk on it. We'll just put the radio on it and see if the radio gives off.
There you go.
Treadmill
Good
gives off
job.
radio.
Good job.
Okay, so we won't turn it on or anything, but stand up there and see if that screen gives off. Up there. A little bit. Back it up a little
But
bit.
it closes this. It closes that. It's just
It's
not
pretty
working.
quiet, isn't it?
It's a hot.
How about over here? Oh, that's a little more.
I want to run.
Ooh, something is. Oh, that control panel is. So does that treadmill give off radio waves? Yes? Very good. All right, who wants to open the door for us? We'll see you, Kevin. Have a good evening.
Thank you.
Okay. See you guys.
Okay. Oh, you got to close it. So you open it, and then you can close it, unless you want to close it. You want to? Okay, you can close it. So everybody remember the rules.